Now,
Yeah.
start. Yeah. Ready.
Ready? Okay, I can see myself. All right, so, well, I said try to read chapters 4 and 5 for the next 2 weeks. I think realistically today we'll actually talk about chapter 4, which is about probability distributions for vectors. So what we saw the idea of a probability distribution for a single variable, so where essentially you have a value of a variable and you have its probability, and for example you have something like a Gaussian distribution that would look like that, and that gives you the probability that this variable x assume any of these values of the y, right? So same thing you can do for a generic number of variables, or as we would say, vector. So vector, you can think of a vector as in the first instance as a list of numbers. So, and that's the form in which our data comes in most of the time. For example, you could have like an EEG or an electrophysiological trace from time 1 to time t is a vector. The count of so the latency in a behavioral experiment across trials is a vector, and so on and so forth. So your object space discrimination index, indices across trials, etc. What we want is to find a definition of probability distribution. Okay? And so we have to see like what stays similar and what changes when you consider that. So go back to the probability distribution for a single variable. So what this is, in a nutshell, is the idealization of a histogram. So suppose that you repeat this experiment many times, and you actually have many readouts, and you count how many readouts happen. You discretize x, so you subdivide x, the possible values for x in bins, and you will get something like this, right? So where the histogram is something empirical. What does it mean? It's something that you measure for data. The probability distribution is an idealization. Something that captures sort of the essence of the histogram but doesn't really exist in reality. So the concept of a histogram will be very important for all this. So what's the equivalent here? Well, you need to have a histogram with multiple dimensions. Two-dimension, so you have a plane. What you do, instead of a binning, you essentially make a grid. Again, so suppose that you measure now two variables. For example, you listen to two neurons. You look at the activity of neuron 1 and neuron 2. Discretize. Now, for each repetition of your experiment, your result is two numbers. And so you get an entry here, and then essentially you have a table where you say, suppose that so I get in 5 experiments cell 2 cell 1 fired 2 spikes and cell 4 fired 4 spikes, so this happened 5 times, and so on and so forth. You repeat, suppose you repeat this experiment many, many times, you can fill this counting table. Right? And you will likely get something that, and you can see that, so this table here has a hotspot, right? So where actually everything else is 0 except for this region. Okay. So this is what is in psychology textbooks called contingency. In mathematical terms, this is called joint probability distribution. Right? Now, the histogram is important because so if I bin the values for this variable in n, I make it n bins. So the total number of bins in a unidimensional histograms will still be n bins. Here, two variables. If each variable is bin in n bins, the histogram will have a total number of bins, which is the number of bins squared. It's a table, right? It's a square. So if I have 8 bins here, 8 bins here, I have 64 legal squared. And if you increase the dimensionality, so if you have a bigger vector, you have more variables you're looking at, then the dimensionality in the total number of bits increases. This is an important thing. Actually, just to give you a spoiler, so the reason why it's important is because the more bin you have, the more difficult it is to approximate this probability distribution from an experimental point of view. Essentially, you have a lot of different combinations that you need to evaluate experimentally. So that means the number of trials you need is going to be of the order of the number of bits in the histogram. It's going to be of the order of the number of bins in the histogram, which is the number of bins, the dimension of the okay.
But that offers to me, but you can decrease then the number of trials that you need if the bins are discrete, linear.
Yeah, you need to go for a coarser discretization.
Yes, but what I mean, if you have a linear binning, then you can do like clustering and everything, right? Because then isn't like that means in a way 2 and 3 you could downsample.
Well, you need to have smart ways to reduce the number of bits. For example, if you know that most of the bits are going to be 0, you might actually find a smart way to take that into account. But if my goal is to evaluate in the most general possible case this entire histogram, I have this. This is known as the curse of dimension. If you Google it, it's actually a okay. So, which suggests that, I mean, everything in modern neuroscience is about multivariate data analysis, but should always think 2 or 3 times before embarking in something that has a very complex resolution. So, example of this is something close to home here, Pedro spike sorting. So that is typical case of a multivariate probability distribution because here we are sampling data from 4 different terminals, so who ones of you have been doing better recording will recognize this figure. So we have 4 wires, and each wire gets a slightly different version of the, for example, a spiking wave. And so, and if we plot here, so that means that if we just take the maximum amplitude of spikes, we plot the probability distribution across all spikes, we have a 4-dimensional histogram. Which means we cannot plot it on paper or on a computer screen. So what we do on a computer screen is typically plot the 4 projections on the 6 possible projections, so x1 versus x2, x1 versus x3, x1 versus x4, x2 versus x3, and so on and so forth. Right? So these are projections of something that exists in a 4-dimensional space. So originally at the beginning of tetrode recording, so we used to do spike sorting in a completely manual way, which means people were using a computer program. At that time we had X-Class. That was the grandpa of X-Class, Matt Wilson wrote it. That would plot all these blobs, and then you would go and manually draw contours to identify the blobs, and then you would move to a different projection and do these contours again. Okay. So this is still, because you work on projections, it's still inferior to an automated spike sorting algorithm that sees directly in 4 dimensions. Right? So that is to say, to give you an example, so suppose that I do things in 2 dimensions so that I can plot the entire thing. And in 2 dimensions, I have a blob that looks like this. So if I plot the projection on this dimension here, yes, this projection on this dimension here. So if I cut the cluster based on the 2 projection, what I will do is make a cut like this and a cut like this. And so my cluster would essentially be a square. And there's no way I can do, by working with projections, the only thing I can do is get some sort of square, or in multiple dimension what we would call a hypercube. So all the clusters that you, or a hypercylinder, but all your clusters that you would make with X class or N class are essentially cylindrical. You cannot see because it's a 4-dimensional cylinder, but it's a cylinder, which is not the right shape. So when you do manual refinement in spike sorting, you have to keep in mind that you might think that it makes sense, but you are doing it based on a distorted perspective. So I said joint probability distribution. So this is the mathematical symbol function. It's called, for example, for function of x. Okay. And then you do the typical things that mathematicians like to do, like integrals, which means I'm going to sum. For example, if I want to have the total probability that x is included between a and b and y is included between c and d, I have to summate, or for a continuous function, integrate this function between a and b and b and c. Okay, so any questions? So now,
Did you understand it well enough, Steve?
Yeah, stop me at any time. I mean, this is for you guys, so that is not because I have to.
I'm surprised that actually I am.
Huh?
I'm surprised that I am following, even if I'm separate.
Yeah. So you have a function, but let's keep it two-dimensional. A function of two. This is the joint probability distribution. Joint probability distribution contains all the possible information. That's the fullest characterization of your data possible. But, as we said, it's affected by the percentage. So one thing that I would like to know is how I go from the full probability distribution to a probability distribution that is only for one variable. So I can say, yeah, I'm recording x and y, but yeah, I don't care about y. I only care about x. I want to know probability distribution just for x that ignores this data. How is this related to this? What I have to do is that for each value of x, I sum, or I integrate over all the possible values of y. I go from all the possible means. If I do this, I go from the joint probability distribution to what's called the marginal. This is the marginal. And this operation is called marginalization. Marginalization is a way to make probability distribution lose a value. Okay? Just sum over all the possible values. So, joint probability distribution, the empirical version of it is a contingency. So, suppose we observe spike counts for two neurons recorded simultaneously over an interval of 100 milliseconds, and so x and y represent the spike counts. So then I represent the joint distribution by counting how many times I get any combinations of spike counts, 0 and 0, 0 and 1, 0 and 2, 1 and support, and I divide by the total number of trials in my experiment. Okay? Which means all these numbers in this table, or this matrix, as we would say mathematically, must add up to 1. And again, so this is the contingency table, so it's the empirical version of the joint distribution. I can marginalize, I can get a single variable instead. And so there is a lot of things. Another thing that we have to discuss, so this is what's called the expected value. What what's the expected value? Well, I told you that, so there are histograms or contingency tables, and those are an empirical concept, and then there are probability distributions that are an idealized concept. Now, histograms have a mean. What's a mean? It's the average value. That's sum of I, xi, divided by n. Empirically, so you have histograms and you have means and so idealized, you have probability distribution and you have what's called expected values. What's the expected value is the sum or an integral over the probability distribution multiplied by x. That means we make a weighted sum, the possible values of x weighted by the value of the probability distribution. So these two things would be the same thing if I had an infinite sample. If I made an experiment in which I was doing an infinite number of trials, then you would get that the mean would tend to the expected value. Okay? So the expected value is an operation we perform on probability distribution, and mean is an operation we perform on data. Keep in mind this distinction. Okay, and well, yes, and it's linear. I mean, you look on the book, there are a lot of nice mathematical properties where, yeah, it's linear, which means the expected value of a sum is the sum of the expected values. And also you can multiply it by the constant, and then the constant gets out of the expectation. And yeah, you have very nice properties that you can demonstrate. Yes. Do that. So here there is an important concept, and this we touched upon already, but I want to say it again because so you have joint probability distribution. And one possibility, which doesn't have to be, but could be, is that you can write this as the product of two functions of one variable. This is a function of x and y. I write it as the product of function of x and function. To go to our examples before, that means say that this is x, and this is y. And each one of them has their marginal distribution. Then the two-dimensional histogram of the joint probability distribution is just the product. So to find the value of this point, I take this value, take this value, then I get the probability distribution that likely, in this case, would look like a circular plot. in this case, we say that the two variables are statistically independent. So that means that the two variables don't care about each other, which we have to explain. Actually, I can explain it. What does it mean that they are independent? Well, suppose that you have these two variables that I'm reading out, and suppose that I tell you the value of x. Value of y, I don't tell you. So that means that y remains a random variable, and it has still a probability distribution. For example, I could be here with x. What I do is essentially I do a cut through this distribution, so this will look like a bump, right? So I can cut it with a knife. What I get will be a shape like that. And the important thing here is that wherever I make the cut, I always get the same shape. So that means the probability distribution of y doesn't depend on the value of x, once I know the value of x. And likewise, the probability of x doesn't depend. This is always a symmetric property. So if x is independent of y, y is independent. So, you see why this is the right definition. And I mean, mathematically you can see it, because if you have this form, marginalizing over y, so integrating over y, gets rid of this part, but leaves alone this part. So this will be the probability.
I don't get quite the relationship between the equation 4.2 and 4.3. The lower one is the formalization in terms of independency of the first one, kind of?
Yeah. So maybe it's clearer if I introduce another concept, which is the concept of conditional probability, which is what I actually was saying in words before. For example, you have the probability of y given x. This is a function of y alone, but for a fixed value of x. And that would be the joint probability distribution for x and y, but I need to normalize it. Why do I need to normalize it? Because so you have a bump, and so if I make a cut here, or I make a cut here, I get the same shape, but with different amplitude. And remember, a probability distribution must add up to 1. How do I make it add up to 1? Is by dividing by all sum over all the possible values. Okay. And if you remember the definition, this is the marginal distribution. the marginal distribution. So this is the probability of distribution for y after I told you the value of x. Okay. So suppose that we are in a condition in which you have a faulty communication channel. So like you are, somebody is telling you the result of your experiment for x and y by phone, but the line is disturbed, so you learn about x, but you couldn't really hear what the value of y was. Then in that case, you can say yes, okay, so that if I know x, so this must be give or take the value of y. But now the point is, if they are statistically independent, so if I told you x, I told you exactly nothing about y. If there is a statistical dependency, however, so if the histogram, for example, looks something like this for x, y, then I know that if x is high, then chances are that y is high as well. And if x is low, then chances are that y is low as well. Or as we would say, x and y are correlated. I'm already introducing another important concept, which is correlation. So if two variables are correlated, then they are not statistically independent. However, the definition of correlation is a little bit narrower than the definition for statistical dependency. So, okay. So then, here you have an important theorem. And this is a theorem for independent variables. And this is essentially the reason, this theorem is essentially the reason why when you go to the lab, you repeat an experiment multiple times. And so that is what enables us to do science and what causes you to spend a lot of time in the lab. You can see. So, what's the, well, I told you the expectation of a sum is the sum of expectations. Then I can introduce another concept, which is the variance of x. I can see the variance of x as the expectation of x minus x mean squared. For the mean. Now, the variance, suppose that now I have a bunch of statistically independent variables. For example, independent variables should be the outcome of the multiple trials in an experiment if you're having a good day. If something is wrong in your experimental setup, it might introduce correlations between the outcomes of different trials, and then all the hell breaks loose. Suppose that everything works perfectly, and this is and so that all the variables are independent. So I could ask, what's the variance of the mean of all the variables? So, and that is going to be 1 times variance yes. So this is the variance. So this is, if I write it, so let's write it it's incomplete. So this is the expectation of some variance. Let's call this mu. Mean variance So, what's the point? That this, and there is a sum. Yes. The point is I can take the mean and I can take this 1 over n squared out of this equation. I the variance of x. That's nice. Why is it nice? Well, because how many terms do I have here? I have n terms. Here I have 1 over n squared. So that means that this whole thing scales with 1 over n, which means the noise in my data, or the statistical variability, decreases with the inverse of the number of repetitions, which is the basic reason why we do many repetitions. So,
But wait, but we do many repetitions, independent repetitions.
you have to make many independent repetitions.
And that's why the dependent repetitions are the difference. What would be a difference between the dependent and our experiments? Think about what do we repeat that's dependent, and what is our replication that's independent. So what are the two things that we repeat? We actually mainly do independent repeats because I tested dependent repeats with Hussein and we noticed it didn't work. Let's see if you get it. So if I take one animal and test the same animal 10 times, it's a dependent repeat. And that's why you can't just take one animal, test it 10 times, pretend it's 10 tests. You can average now for an animal.
Okay. If you have only one animal, you could say that if you take the trials as a characterization of what that particular mouse Joe is doing, those are independent trials.
Yes.
However, if you have 3 mice, Joe, Peter, and Robert, and each one does 10 trials, then you cannot say that those 30 trials are independent trials in terms of giving you a characterization of what the universe of mice.
That's why in our case of, for example, object space, if you repeat, so for example, we are repeating partly with intellectual ability, if we at the end collapse it, which may actually turn out to be, so that's what people, and then you first average the repeats within animals, and that will decrease the variance for the animal, and then you can use that value. But then, better example. Since a lot of you are doing the mouse stuff, or you're doing mouse protocol with rats, we currently, when we do a graph where we have 5 days of discrimination index, and in each day it's 5 trials. Currently, how we do it with Excel, Excel really is taking the animal and the repeated trials per animal, and that's why we get 40 values average. Let's say for 8 animals with 5 trials, get 40 values per day. That's wrong. So that we now let Excel do, but on the long run, if you want to do it right, you have to average the 4 repeated trials for an animal to 1 daily value for each animal. And then the 8 animals are your repetitions, or your independent values. So that's why you first have to average that, and then, because else you're mixing 2 different types of repeats that are not.
The between and within comparisons, right?
Yes, yeah, that's by dependent independence.
So, if your variables are not dependent, then when you sum the variances of 2 variables, an extra term appears. This extra term depends on something called the covariance of the 2 variables. What's the covariance? It's the expected value of the product of the 2 variables where we subtracted the mean. You always want to subtract the mean so that you work with variables that have 0. So covariance is the first measure of statistical association. Statistical association is the opposite of statistical independence. And this measure of statistical association shows up here, where you are trying to compute the variance of your mean, which is the number that in the end you report in your paper. Okay? And that essentially ruins all your gilded castle. So that is something that if you have to live. On the other hand, if I'm interested in the association between X and Y, which could be, for example, the amount of drug I inject in the mouse and the memory retrieval, and then this covariance is exactly what I need to look for. Right? Sure. So covariance, it's a measure of statistical association. It's slightly less useful in that it depends on the scale of the variables. Which means if I multiply one variable by 10 or by 60, suppose that I go from spikes per second to spikes per minute. Just because I can't get the variance also scales up. We typically prefer to work with something called the correlation coefficient, or Pearson correlation, which is the covariance normalized by the product of the variance of X and the variance of Y. And the nice thing about it is that now this number will always be between -1 and 1. Where 1 means perfect correlation, which means that the data actually lie on a straight line, and you can only, so if you know the value of x, you know the value of y exactly. And -1 is the exact same thing, except that now the line has the opposite indication. Perfect correlation and perfect anti-correlation. And usually we use the symbol rho. And again, so this rho correlation coefficient is an idealized quantity that comes from the probability distribution. The equivalent thing, so its estimate from the data, equivalent empirical thing is called the sample correlation. And this is just expressed in terms of the readouts. Okay, so again, you have an ideal concept, and you have an ideal concept, and you have an empirical concept. So the ideal concepts are useful because you can do precise mathematics on them. And the empirical concepts are useful because they have a slightly clunkier form, but it's something I can compute from the data. I would write a little MATLAB or Python code that computes the sum and get the number. And sometimes also known as rho hat. But the last, here, it goes into numerical examples where it competes with stuff. So, just to finish this topic, I just told you that a correlation is a slightly narrower concept than statistical dependency. And for example, you can have situations in which variables have a correlation of 0 to variables, but they are far from being statistically independent. And one case, so this is true, for example, in all the cases in which the probability distribution for x and y is symmetrical as circular symmetry around the center, around the origin. Suppose, for example, that you have a donut shape probability distribution. So all the values that are only the values inside this ring are greater than 0, and elsewhere it's zeros everywhere except for the inside of this ring. Well, you can compute this. You find out if you compute the Pearson correlation, this is 0. However, this is far from being statistically independent, because if x is here, you know that y is confined in this interval. If x is here, you know that y can only be either here or here, and so on. So, if knowing the value of x, by changing the value of x, you get a completely different distribution. This is an example of two variables that would be uncorrelated but dependent. So it's a case that you won't come across too often. Okay. So now we have to go into regression, but so if there are any questions so far. Okay. How is it? Can people more or less follow? Is it too fast? Okay. So
can I give a tip what I think would help?
yeah.
So this, I've been telling people the cult learning cycle, you know, you guys are making, I really want to do this one, we want to find out which learning types are here. So the book I see is written for, it pretends to be written for neuroscientists, but the book is clearly written for more theoretical people in a way that it starts with theory and then ends with the example.
Well, yeah.
If you, for biologists, understand stuff better if you start with the example and then explain why we now need the math. It's just how biologists learn. So, well, on average, there will be exceptions, but on average,
This is
no, it's actually not about, it's the other way around. You have learning types, and then the learning types will select certain jobs. So that's why, because the worst of the surgeons, because the surgeons are practical, so you first have to explain in a way and make them build a tetrad, and then they could ever think about even the math. But and it's just that on average, biologists will be practical theoretical. So they need to start with practical, and then you can use the theory. But I could follow, and I missed the last two sessions. So I think that way I found it very well explained actually.
So yeah, so basically what I would advise is that, so basically we covered the first 10 pages of this chapter, and actually this is an extremely important chapter because it goes into, it basically covers correlation, regression, and Bayesian inference. So those are essentially the most basic concepts.
Yeah, especially coming to Bayesian, I think that's a whole separate session.
Yeah. I mean, well,
next time regression.
Yeah, regression, and we can get started. I mean, that regression that is actually, it does it quite nicely because it actually puts it all in the framework of correlation.
Yeah.
So it makes it become like a very straightforward consequence of what we said so far. So basically, here's this is what's called linear regression, which means coming up with a linear model of data, so the relation, a linear relation between x and y, and we'll see how this linear relation is actually determined by the correlation coefficients and the variances.
The other thing I could recommend for just general reading, so I personally also benefited from reading 2 different books to the same topic. And this seems now actually quite similar to this one book which I read a few years back, it's a very good book. I want to say it's called Statistics of Biomedical or something. And the author is the guy who invented graph algorithm. And so it's not that big, so it would be also achievable, I think, to read it in parallel to this one. It's really a small book actually, and it goes through very similar concepts. So maybe, but again, with good examples, very very easy to understand. So I really read it by myself, and it was fine. I really just read it, and it's readable. And so that could be another way that to prepare or post-process, that you afterwards read it in this other book. I should look for my copy.
Okay.
Our Skype, yeah.
No, not Skype, it's a YouTube.
He's rude. Oh yeah, right.